An expiration date is a simple mark on a label. It represents a promise from a manufacturer. Until that date, quality and safety hold, if stored correctly. For foods, that means taste, texture, and nutritional value. For medicines and chemicals, including poisons, the date carries more weight. It guides effectiveness and, crucially, safety. What happens after the date passes? Does a poison simply fade into harmlessness, or transform into something even more dangerous? The answer is not a simple yes or no. Science shows it can do either. The outcome is a complex chemical story. First, understand what that date truly signifies. It is not a magic moment. It marks the end of rigorous stability testing, not an instant of chemical collapse. Manufacturers store samples under controlled heat, light, and humidity. Over weeks, months, even years, they analyze how actives hold up. The date often aligns with a potency threshold, commonly about 90%. It also flags when undesirable breakdown products begin to appear. It is a conservative boundary to ensure reliability, not a prediction of sudden collapse. We meet toxins everywhere: cleaners, garden pesticides, prescription drugs, and industrial compounds. Sitting on the shelf, they keep reacting, slowly shaped by their environment. Chemicals obey entropy, from order to disorder. We call this chemical breakdown, degradation. Actives slowly change form or split into smaller fragments over time. It is gradual. Heat, light, water, and air speed it up. Moisture drives hydrolysis. Water wedges bonds apart. Oxygen causes oxidation, like rust or a cut apple browning. Sometimes potency falls and risk drops. Other times fragments become new, potentially more toxic chemicals. Are degradants less toxic, more toxic, or the same? It depends. The label shows the original. An expired bottle can be a complex mixture. Structure and storage history decide the outcome. Chemical stability is how resistant a substance is to change. Stable chemicals endure, unstable ones change quickly. Think quartz, millions of years, versus a reactive compound that shifts in minutes. Manufacturers invest in stability studies. Samples sit under precise temperature and humidity. Some at room temp, others accelerated hotter. Analysts track active concentration and identify breakdown products. The date lands near the 90% mark. For poisons, concentration is only half the story. The other half is what the toxin turns into. Degradant toxicology matters for humans, animals, and the environment. These assessments take time and resources. Fragments do not vanish. They become new molecules. Best case, breakdown detoxifies. Smaller, simpler fragments may be biologically inert. They no longer fit biological targets, but breakdown can also bioactivate. Consider organophosphates like parathion. Oxidation can convert parathion into paraoxon, more potent and dangerous to mammals. Warm, sunny storage can turn a bottle into a greater hazard even as the original concentration drops. Tetracycline once degraded to a kidney-toxic product. Formulations improved, but it proves breakdown can create harm. Studies confirm unpredictability. Caution is wise. Pesticides are heavily studied due to broad exposure. Organophosphates can cut both ways. Under heat and humidity, malathion can form malaoxon, significantly more toxic. Some herbicides like glyphosate degrade to AMPI, SOITES, barbic-9, generally less toxic depending on conditions. Environment controls speed and pathway. FDA/DoD testing showed many sealed drugs retain potency years past expiration. Common tablets often last. Liquids and biologics are riskier. Without specific data on a specific bottle, you cannot know the path. It enters chemical uncertainty. With poisons, public health guidance says, do not gamble. Storage environment directs chemical destiny. Lab control is rarely matched in garages, sheds, or under sinks. Real-world conditions constantly shift. Heat accelerates reactions. Hot sheds speed breakdown. Cool darkness slows it. Sunlight, especially UV, breaks bonds via photolysis. Opaque packaging protects from light not used in tests. Heat plus light, powerful and unpredictable. Moisture drives hydrolysis. Broken seals invite humidity. Solids can degrade when they absorb water. Formulation impurities and even containers can react, adding yet more variables. We have great tools, but limits remain. Real-world variability exceeds standardized tests. Standards cannot cover every scenario. Most products are mixtures whose components interact over time. One degradant can accelerate another. Networks get complex fast. Years later, contents can diverge far from the label. Long-term toxicology on degradants often does not exist. Models help, but they are estimates, not certainties. Thus, the responsible stance is precaution. Beyond the date, you enter educated guesswork and risk. Practically, treat expired poisons with caution. The chance of increased toxicity is not worth the risk. Simple rules for home, garden, and garage. Use within the manufacturer's timeframe. Buy only what you need. Store properly. Follow label instructions. Cool and dark slows degradation. Avoid temperature swings and direct sunlight. Keep products in original containers. After expiration, think disposal. Never pour toxins down the drain or gutter. They can harm waterways and wildlife. Use local hazardous waste collections or drop-off facilities. Respect the limits of knowledge.